August 7, 1942. 16,000 U.S. Marines wade through chest-deep surf toward a name most of them can't even pronounce, Guadalcanal. A steaming, insect-choked jungle in the Solomon Islands. Their mission sounds simple on paper: capture an airfield the Japanese are building. Within 36 hours, they do it, with surprisingly light resistance. The Japanese melt into the jungle. Mission accomplished, or so they think. But the real nightmare is only beginning. The airfield they've taken isn't finished. It's nothing more than a rough strip of cleared earth, and that earth is alive. In the Pacific heat, it bakes into something harder than concrete. When the monsoon rains come, it dissolves into a slop with the consistency of chocolate pudding. The Marines stare at the ground beneath their boots and realize, this runway could kill them all. Because here's the truth no one told them about island warfare in the Pacific. You don't win by holding the ground. You win by controlling the sky. And to control the sky, you need a working runway. The Japanese know exactly what they've lost. Within days, their bombers are hammering Henderson Field, the name the Marines give the strip, in honor of a pilot killed at Midway. But the bombs aren't the worst part. The mud is. Every time the skies open, the runway turns to soup. Wildcats and dauntless dive bombers, the Marines' only air cover, sink into the muck. Mechanics watch helplessly as landing gear vanishes into the ground. One pilot throttles up for takeoff, his wheels carving trenches 4 feet deep before the plane even moves an inch. He never gets airborne. 20 minutes later, the Japanese bombers he was supposed to stop arrive, unchallenged. Desperate engineers try everything: filling, packing, leveling, anything to keep Henderson Field alive long enough to fight another day. The Marines try everything to keep Henderson Field alive. First, they haul crushed coral from the nearby beaches, spreading it across the runway. It looks solid, until the next downpour washes it away. Then they try pierced steel planking, borrowed from bridge-building stockpiles. Under the relentless tropical sun, the metal warps and buckles like tinfoil. Next, they roll the soil flat with heavy compactors. The rollers don't last long. They sink and get stuck in the same mud they're trying to tame. By mid-August, Henderson Field works, barely. Operational maybe 3 days out of 7, depending on the weather. And when it rains, the Marines are naked before the enemy. No air cover means Japanese warships can shell the beaches at will. No air cover means enemy reinforcements can slip ashore under cover of night. The math is brutal and simple. Without a runway that works in all weather, Guadalcanal will fall. If Guadalcanal falls, the entire Pacific offensive grinds to a halt, for a year, maybe longer. Back in Washington, that crisis lands squarely on the desk of the U.S. Army Corps of Engineers. Desperate radio messages flood in from the Pacific. We need a solution, and we need it yesterday. The Corps isn't starting from scratch. They've been wrestling with the soft ground runway problem since before Pearl Harbor, testing designs in Louisiana swamps and on Alaskan tundra. Every experiment has failed one way or another. Now, they're watching those failures come to life, 7,000 miles away, in the jungles of Guadalcanal. Their first real attempt had come back in early 1941. Square mesh track, a welded grid of steel bars, like chain-link fencing made from rebar. The idea made sense: build a rigid skeleton to spread the weight of planes over a wider area. At Langley Field in Virginia, they rolled a B-17 bomber over the prototype. The test lasted seconds. The mesh folded like paper under 30 tons of weight. The steel simply wasn't thick enough. But making it thicker would make it too heavy to move, requiring an entire cargo ship just to haul one runway. Shipping enough steel mesh for a single runway would take an entire cargo ship. Clearly, that wasn't the answer. Next came the Hessian mat experiments in the spring of 1941. British engineers had reported success in North Africa using burlap fabric coated in asphalt as makeshift roads. American engineers thought, if it works for trucks, why not aircraft? They soaked thousands of yards of heavy jute fabric in boiling asphalt, rolled it out across soft ground at Wright Field in Ohio, and began landing tests with P-40 Warhawks. The first landing looked promising. The second carved ruts. By the 10th, the matting had ripped apart completely, clogging landing gear with asphalt-soaked burlap. The idea was dead by June. The Coralline gravel approach looked better, at first. It mimicked the natural hardpan surfaces common across Pacific islands. In July 1941, engineers built test strips using crushed coral mixed with volcanic rock, compacted until it was hard as concrete. For 3 weeks, it worked perfectly. Then came the rain, 6 inches in 2 hours. The surface dissolved into slurry. Deep gullies appeared, some deep enough to hide a man. Worse, once coral breaks down when wet, it can't be recompacted. You have to start from scratch. The next breakthrough seemed to come with pierced steel planking, PSP. Originally a British invention for quick road building, these were flat steel sheets, 10 feet long and 15 inches wide, perforated to reduce weight and add traction. By August 1941, the U.S. was testing PSP for runways at Bowling Field. The engineers loved it. You could shingle a runway in days instead of weeks. But tropical heat had other plans. Steel expands under the equatorial sun, and soon the PSP began to buckle and warp, forming razor-edged ridges that could tear the landing gear off incoming planes. Pilots said landing on PSP in the heat felt like touching down on a washboard at 80 miles an hour. By the fall of 1941, the Army engineers were out of ideas, and out of time. Then came December 1941. Pearl Harbor. It wasn't just a military disaster, it was a wake-up call. The Pacific War would demand solutions that didn't exist yet. The U.S. Army Corps of Engineers sent out an urgent message to every major American steel manufacturer. We need a runway surface that can be installed in days. Support aircraft up to 50,000 pounds. Work in mud, sand, or coral. Survive tropical heat without warping. And be light enough to ship halfway across the Pacific. On cargo vessels already crammed with tanks and ammunition. The race to invent the impossible had begun. Carnegie Illinois Steel Corporation, based in Pittsburgh, wins the contract. Their lead engineer, James Marston, studies every failed design and realizes something no one else has. Everyone's been trying to recreate concrete, to fight the mud. Marston's insight is simple and radical. Don't fight it. Float on top of it. He begins sketching a surface not as a rigid road, but as a flexible steel carpet, something that could move with the earth instead of against it. By February 1942, Marston's team produces a prototype. A steel plank, precisely 10 feet long and 15 inches wide, but unlike anything before it. Its thickness, 3/16 of an inch of high-strength steel. Thick enough to resist bending under a bomber's weight, yet thin enough that each plank weighs only 66 pounds, light enough for 2 men to carry and lock into place without machinery. Across its surface, engineers punch rows of oval holes, giving it the look of an industrial cheese grater. The holes aren't for show. They serve 3 critical purposes. Reduce weight by nearly a third. Let rainwater drain through, instead of pooling on top. Add traction, giving aircraft tires something to grip. But the real genius lies in the edges. Each long side features a precision-engineered interlocking design. One edge has a raised lip with a hooked end that curves upward. The opposite side has a matching channel. Lay 2 planks side by side, and the hook slides perfectly into the groove, locking with pure mechanical pressure, no bolts, no welds. The connection is strong enough to carry a 50,000-pound aircraft rolling over the seam, yet flexible enough to bend over uneven ground without breaking apart. The short ends use a different joint, a simple overlap, where one plank slides under the next. That overlap creates a seamless, continuous surface, no gaps big enough to catch a wheel. And as weight presses down, the planks tighten together instead of separating. In March 1942, the Army puts Marston's invention to the test at Camp Claiborne, Louisiana, a swamp chosen specifically for its awful, sinking soil, nearly as bad as Pacific Island mud. Engineers lay down 1,200 square feet of Marston's interlocking planks directly on top of the unprepared, swampy ground. Then they roll a fully loaded aircraft across it. Carnegie Illinois Steel Corporation, based in Pittsburgh, wins the contract. Their lead engineer, James Marston, studies every failed design and realizes something no one else has. Everyone's been trying to recreate concrete, to fight the mud. Marston's insight is simple and radical. Don't fight it. Float on top of it. He begins sketching a surface not as a rigid road, but as a flexible steel carpet, something that could move with the earth instead of against it. By February 1942, Marston's team produces a prototype. A steel plank, precisely 10 feet long and 15 inches wide, but unlike anything before it. Its thickness, 3/16 of an inch of high-strength steel. Thick enough to resist bending under a bomber's weight, yet thin enough that each plank weighs only 66 pounds, light enough for 2 men to carry and lock into place without machinery. Across its surface, engineers punch rows of oval holes, giving it the look of an industrial cheese grater. The holes aren't for show. They serve 3 critical purposes. Reduce weight by nearly a third. Gervonta Davis, Tank Davis, Gervonta Davis KO, Jake Paul fight, Gillette rainwater drain through, instead of pooling on top. Add traction, giving aircraft tires something to grip. But the real genius lies in the edges. Each long side features a precision-engineered interlocking design. One edge has a raised lip with a hooked end that curves upward. The opposite side has a matching channel. Lay 2 planks side by side, and the hook slides perfectly into the groove, locking with pure mechanical pressure, no bolts, no welds. The connection is strong enough to carry a 50,000-pound aircraft rolling over the seam, yet flexible enough to bend over uneven ground without breaking apart. The short ends use a different joint, a simple overlap, where one plank slides under the next. That overlap creates a seamless, continuous surface, no gaps big enough to catch a wheel. And as weight presses down, the planks tighten together instead of separating. In March 1942, the Army puts Marston's invention to the test at Camp Claiborne, Louisiana, a swamp chosen specifically for its awful, sinking soil, nearly as bad as Pacific Island mud. Engineers lay down 1,200 square feet of Marston's interlocking planks directly on top of the unprepared, swampy ground. Then they roll a fully loaded aircraft across it. Would you like me to continue with the test results and how this invention became known as the Marston Mat, the steel that helped win the Pacific? Here's a refined, cinematic version of that passage, tightened, clear, and visually rich while keeping every factual detail intact. Carnegie Illinois Steel Corporation, out of Pittsburgh, takes the contract. Their lead engineer, James Marston, studies the long list of failed designs and sees the problem immediately. Everyone's been trying to build concrete out of steel. His realization is simple, but revolutionary. Don't fight the mud. Float on it. Marston sketches something new, a surface that behaves more like a metal carpet than a road. Flexible. Lightweight. Fast to assemble. By February 1942, his team has a working prototype. A steel plank, 10 feet long, 15 inches wide, and 3/16 of an inch thick. That small change in thickness is everything. Strong enough to carry a bomber, yet light enough that 2 men can carry one plank without machinery. Across its face, Marston punches rows of circular holes, a design that looks almost like an industrial cheese grater. Each hole serves 3 precise functions. Cuts weight by 30%. Lets rainwater drain through. Adds traction for landing gear tires. The real breakthrough, though, is in the edges. Each long side is engineered to interlock, one edge with a raised hooked lip, the other with a matching grooved channel. Slide them together, and they lock with pressure alone. No bolts, no welds. The result, joints strong enough for a 50,000-pound plane to roll over without separation, but flexible enough to conform to uneven ground. At the short ends, a simple overlap joint keeps the planks continuous from end to end. No gaps. No weak points. And as aircraft roll over, the pressure tightens the seams rather than spreading them apart. In March 1942, the Army Corps of Engineers tests the system at Camp Claiborne, Louisiana, chosen for its infamously soft, swampy ground. They lay 1,200 square feet of Marston's interlocking planks directly on top of the mud. Then, a fully loaded aircraft rolls onto the new surface. It doesn't crack, because it isn't trying to be rigid. Each plank can flex ever so slightly, shifting by fractions of an inch, yet still holding its interlocked grip. The entire runway doesn't rest on the ground. It floats over it, like a steel raft, adjusting to the Earth's movements beneath without tearing itself apart. The holes punched through every plank aren't just to shed weight. They create what engineers call a semi-permeable surface. And that's a game-changer in the Pacific, where it rains almost every day. Instead of pooling into slick puddles that cause hydroplaning, the water drains straight through. Yet the holes, each only 2 inches across, are small enough that an aircraft tire, much wider, still feels a solid surface beneath it. To a plane, it's steel. To the rain, it's a drain. Tests at Wright Field in April 1942 proved it. Water cleared 6 times faster on Marston Mat than on solid concrete. The interlocking design solved another problem no one had even anticipated: bomb damage repair. When Japanese bombers cratered a runway, you couldn't just patch Marston Mat like concrete. You had to replace sections. But that was its secret strength. Because the planks weren't welded or bolted, crews could simply unlock the damaged panels, slide them out, and drop new ones into place. At Henderson Field, engineers timed it. A 20-foot wide bomb crater could be repaired and ready for takeoffs again in under 40 minutes, not counting the time to fill the hole itself. A concrete runway would have taken days, plus equipment and curing time. And because the system was so simple, it needed no specialized training. You didn't need engineers, just men who could follow a pattern and work fast. Henderson Field, August 17, 1942. The first shipment of Marston Mat arrives at Guadalcanal. Cargo ships, having dodged Japanese submarines, unload 36 tons of steel planking onto the beaches. The Naval Construction Battalions, the Seabees, get to work immediately, under fire. Zero fighters rake the shoreline as men drag heavy planks across the sand. Their deadline isn't measured in days, it's measured in hours, before the next bombing run. Most of these Seabees have never seen Marston Mat before. A few months earlier, they were carpenters, ironworkers, and equipment operators, building highways and bridges back home. Now, they're in a war zone, assembling a runway from scratch, while enemy aircraft circle overhead. They're being shot at while they work. Coup boxing, Gervonta Davis sparring, heavyweight boxing, Gervonta Davis vs. Jake Paul, Gervonta Davis knockout, boxing sparring, viral boxing video, boxing highlights, Jake Paul training, unseen sparring footage, Gervonta Davis 2025. And the first thing they learn is that 66 pounds per plank sounds manageable on paper, until you're hauling those planks hundreds of yards in 100-degree heat and 90% humidity. Very quickly, a rhythm forms out of sheer necessity. Two-man teams grab planks from the stockpile and haul them to the runway edge. A third man acts as the guide, lining up the edges with practiced precision. The first row goes down easily enough, just steel laid side by side on cleared dirt. But every row after that has to lock into the one before it. They figure out the technique fast. Tilt the new plank at a slight angle. Slide the hooked edge under the channel of the one already in place. Then drop it flat. When it fits right, there's a sharp metallic click, the sound of steel locking into steel. That click becomes the most satisfying sound in the world. It means progress. It means it's holding. It means they're winning, even if just one square at a time. The work comes in frantic bursts between air raids. Japanese bombers are hammering Henderson Field almost every day, sometimes twice. The Seabees learn to read the skies. A single recon plane overhead means bombers are an hour away. When the warning comes, tools drop instantly. Men dive into foxholes as bombs shake the earth. They wait, 10 long minutes, for unexploded ordnance to cook off. Then, just as fast, they're back on their feet. Back to the runway. Back to the rhythm. If a bomb hits the section they've already finished, they unlock the damaged planks, slide them out, and replace them. If it hits a section not yet laid, they fill the crater with coral, tamp it down, and keep building right over it. August 20th, 1942. Just 3 days after the first shipment of Marston Mat hit the beach. A 200-foot by 75-foot stretch of runway is operational. It isn't the full 5,000 feet Henderson Field will need to handle bombers safely. But it's enough for one critical thing. Fighters can take off. It's enough for the fighters. That afternoon, 19 Wildcat fighters and 12 Dauntless dive bombers roar in from the carrier Enterprise. These aircraft, designated VMF-23 and VMSB-232, would soon earn the name Cactus Air Force, taken from Guadalcanal's radio call sign. They land on a surface that hadn't even existed 72 hours earlier. The pilots immediately notice the difference. Landing on Marston Mat isn't like concrete or packed earth. It has a subtle give, a spring-like flex you can feel through the landing gear. Some describe it as touching down on a firm trampoline. That flexibility actually helps. Instead of bouncing hard, planes coming in too fast have some of their impact energy absorbed by the mat itself. By September 5, 1942, Henderson Field boasts a full Marston Mat runway, 5,200 feet long and 150 feet wide. Despite constant air raids and artillery fire, construction takes only 19 days. A traditional concrete runway would have required at least 3 months under perfect conditions, conditions that Guadalcanal definitely did not have. Guadalcanal proved the concept. But what came next revealed the true strategic power of portable airfields. By early 1943, the U.S. military began planning an island-hopping campaign across the Pacific, spanning nearly 7,000 miles from the Solomons to Japan. Every one of those islands would need an airfield, and they'd need it fast. The Japanese strategy relied on turning each island into a fortress meant to hold out for months. Marston Mat would collapse that timeline. February 1943, the Russell Islands. The Marines land expecting fierce resistance, but the Japanese have already evacuated. Within 60 hours of the first troops hitting the beach, the Seabees have completed a fully operational fighter strip made of Marston Mat. Admiral William Halsey is so stunned by the speed that when he flies in to inspect, he asks the battalion commander if construction had started before the island was secured. It hadn't, they'd just become that efficient. The new airfield immediately provides cover for the next advance up the Solomons, cutting weeks of vulnerability down to mere days. August 1943, Munda Point on New Georgia Island. This one is different. The Japanese are still there, entrenched in bunkers overlooking the airfield site. The Seabees lay Marston Mat while under direct fire. They develop tactics that sound suicidal but somehow work. Half the battalion lays planks while the other half provides covering fire with rifles and machine guns. 14 men are killed, 47 wounded, but the runway is operational in just 11 days. Marine corsairs begin launching missions from Munda even as Japanese snipers are still being cleared from the perimeter. By November 1943, at Bougainville, the military begins experimenting with prefabrication. Instead of laying down individual planks. Back in Australia, engineers begin pre-assembling sections of Marston Mat into massive panels, each 50 feet long and 15 feet wide. These huge units are loaded onto LSTs, landing ship tanks, and transported intact to the front lines. When the LSTs beach at Bougainville, cranes lift the pre-assembled panels directly onto the prepared ground. A runway that would have taken 2 weeks to build plank by plank is now completed in just 4 days. By December, Bougainville boasts 3 fully operational Marston Mat runways arranged in a triangular pattern, allowing simultaneous takeoffs and landings no matter which way the wind blows. The production numbers tell the rest of the story. In 1942, Carnegie, Illinois Steel, and 9 other manufacturers produce 8 million square feet of matting. By 1943, output surges to 40 million. In 1944, it reaches 60 million square feet per year, enough to lay a runway stretching from New York to Philadelphia. The demand becomes so intense that it even causes a temporary steel shortage. Tank production is scaled back so the furnaces can focus on turning out more runway matting. January 1945, Lingayen Gulf, the Philippines. Here, Marston Mat is used in ways no one originally imagined. Engineers lay it directly over sandy beaches to create instant piers and access roads for supply trucks. They discover that the mat distributes weight so effectively that it works just as well for vehicles as it does for aircraft. Supply convoys that once bogged down in loose sand can now drive straight from landing craft to inland depots without delay. February 1945, Iwo Jima. This becomes perhaps the most famous Marston Mat installation of the entire war, though few recognize it by name. The volcanic ash on Iwo Jima is so fine and unstable it behaves like powdered sugar. Concrete won't cure properly because ash mixes into it, and compacted earth is impossible because there's no real soil to compact, only dust. Marston Mat becomes the only viable option. Seabees lay it across all 3 airfields on the island even as the battle for Mount Suribachi rages nearby. When the war finally ends in August 1945, military planners assume Marston Mat will fade into obsolescence. In peacetime, after all, there's no rush. Runways can take months to build again. Building proper concrete runways. The steel gets stockpiled at depots across. Then, on June 25, 1950, everything changes. North Korea invades South Korea, and the U.S. military scrambles to re-establish air superiority in a region with almost no usable infrastructure. Those stockpiles of Marston Mat are pulled out of storage and shipped to the Korean peninsula. But Korea is nothing like the Pacific Islands. It's mountainous, brutally cold, with soil that freezes solid in winter. Engineers wonder if steel mats designed for tropical jungles will survive sub-zero temperatures. They soon find out. The steel becomes brittle in the cold, but the interlocking design still holds. The same flexibility that worked on soft island mud now proves vital on frozen ground. When the soil expands as it freezes, the mat flexes upward. When it thaws and contracts, the mat settles back down. No cracks. No separations. Kimpo Airfield near Seoul becomes the proving ground. By September 1950, it lies in ruins, its concrete runways shattered by retreating North Korean forces. U.S. Air Force engineers lay Marston Mats directly over the broken concrete, creating a fully functional runway in just 72 hours. F-86 Sabres are taking off for combat missions while repair crews are still clearing debris a few yards away. By the end of the Korean War, 38 airfields use Marston Mats. The military gives it a new name, PSP, pierced steel planking. The name Marston Mats fades from the records, but the technology remains unchanged. Then comes Vietnam, 1965. The mat returns, nearly 25 years after Guadalcanal. In some cases, it's literally the same steel planks reused from World War II, still strong, still functional. Engineers lay PSP at bases like Da Nang and Bien Hoa, building helicopter pads and expanding runways. The tropical heat, torrential rains, and acidic soil mirror the Pacific conditions it was designed for, and once again, it performs flawlessly. But this time, the story takes an unexpected turn. After Vietnam, Marston Mats finds a new life in civilian hands. Oil companies in Alaska and Canada begin using it to build temporary roads and drilling platforms across permafrost, without damaging the fragile tundra. The same load distribution principle that kept bombers from sinking into Pacific mud now prevents trucks from melting frozen ground. Even environmental groups support its use, because it's removable. Once drilling ends, the mats can be lifted away, allowing the land to recover naturally, unlike permanent gravel roads. Then, January 2010. A magnitude 7.0 earthquake devastates Port-au-Prince, Haiti. The main runway at the international airport remains intact, but the surrounding taxiways and parking aprons are destroyed, creating a massive bottleneck for relief flights. Within days, U.S. Air Force transports arrive carrying pallets of Marston Mats. Yes, it's still being made. Crews lay it across the shattered pavement, reopening vital space for cargo planes loaded with food, medicine, and water. The same technology once used to fight the Japanese Empire now saves earthquake victims. Today, modern militaries still rely on the concept. The U.S. Air Force calls it AM-2 matting, short for aluminum membrane version 2. The material has evolved from steel to lightweight aluminum alloys, but the design remains unmistakable. Interlocking edges, perforated surface, and that same ingenious flexibility Marston sketched out back in 1942. The British Royal Air Force uses it. NATO forces deployed it in Afghanistan to expand Bagram Airfield. It shows up in disaster zones after typhoons, floods, and hurricanes, anywhere you need instant infrastructure. From Guadalcanal to Haiti, from war zones to relief missions, the legacy of Marston Mats endures, a simple idea that changed how the world builds under pressure. On damaged or unprepared ground. The original Marston Mats are still around. You can still find pieces of Marston Mats today, repurposed as walkways, bridge decking, even decorative fencing. On some Pacific islands, sections laid during World War II are still in use, weathered and rusted, but functional after more than 80 years. Wars, we're told, are won by tanks, planes, and ships. That's what fills the history books and documentaries. But the truth is different. Wars are won by the things nobody notices, the hidden logistics, the quiet efficiency, the infrastructure that turns chaos into order. Marston Mats changed the very foundation of how the Pacific War was fought. Before those perforated steel planks existed, capturing an island meant committing to months of construction before it could even be used. You'd seize the ground, then wait, surveying, grading, pouring concrete, and waiting again for it to cure. During that time, your troops were exposed, your new foothold little more than costly real estate. The Japanese understood this perfectly. Their entire defensive strategy depended on time, on forcing the Americans to bleed for every yard and then stall while engineers built airfields. Island hopping, they believed, would be slow and grinding. Marston Mats shattered that assumption. Suddenly, an island captured on Monday could have operational aircraft flying from it by Friday, sometimes within days. That speed changed everything. Islands once dismissed as too remote or too time-consuming to develop now became strategic assets. The Central Pacific Campaign, Tarawa, Kwajalein, Saipan, worked because those islands could immediately support the next assault. The American advance no longer paused to build, it simply kept moving. The numbers tell the story. By the end of 1944, the U.S. military had built more than 300 airfields across the Pacific. Roughly 220 of them used Marston Mats, either in part or entirely. Without it, maybe a third of those could have been built, and each would have taken 3 times as long. That would have meant fewer forward bases, longer flight routes, and less air cover for naval operations. The timeline of the Pacific War could easily have stretched by months, perhaps even a full year. Look at the bombing campaign against Japan. The B-29 superfortresses that ultimately forced surrender flew from the Marianas, Saipan, Tinian, and Guam. Those islands were captured in the summer of 1944. By November, just 5 months later, they were launching massive bombing raids over Tokyo. That was only possible because engineers could lay Marston Mats runways strong enough to handle the heaviest bombers in the U.S. arsenal in a matter of weeks. If they'd had to wait for concrete, those missions wouldn't have begun until mid-1945, and the war's end might have looked very different. There's a deeper lesson here about innovation under pressure. Carnegie, Illinois didn't invent a new material or a revolutionary process. They simply asked smarter questions. How do you make strength without rigidity? How do you make lightness without fragility? How do you make something complex simple enough that exhausted men under fire can assemble it in minutes? The brilliance of Marston Mats lay in its simplicity. Steel planks that locked together, holes that drained water, flexibility that absorbed impact instead of resisting it. Historians often describe the Pacific War as a war of aircraft carriers, submarines, and logistics. All true. But beneath all of that, it was a war of engineering, of problems solved under impossible deadlines. Marston and his team at Carnegie, Illinois may have saved more lives and shortened the war more effectively than any weapon. Not through destruction, but through construction. They turned mud into runways, jungles into airfields, worthless islands into launch pads for victory. Those perforated steel planks with their simple interlocking edges didn't just build runways. They built momentum. They built possibility. They built the future.